Good evening. Seeing that picture was really depressing. You wouldn't even believe that it's the same person, right? Yeah. In the meantime, I got so old that one day when I visited a museum of natural sciences, they wanted to keep me as an exhibit. Yeah. So as the title says, it will be confessions, lots of confessions. So let's start with the first one. 30 years ago, while I was in my faculty, in my studies, I was a mediocre developer. And in the meantime, I just got older. And during all this time, I was, oh, that's not very good, but it's written whiteboard versus keyboard. The thing that you don't see is whiteboard over keyboard. So it will be 3 chapters. The first thing is, yeah, that's me during studies, yeah. No, just kidding. During those years, I was really fascinated, and I envied all those colleagues of mine who you probably had colleagues of those in faculty who were splitting their screen in 2 during lab works. Half of that was the editor where they were writing code, and the other half was the assignment. And they were literally looking at the assignment and with their eyes on the assignment, and they were typing the code just as they were reading. And they were typing so fast, and they were writing code so fast. And I always thought that's the superpower that one day I will have as well. I will learn to type faster, and then I will get a good programmer. So, but then 1 year later, I got my first paid job as a software engineer. And then I realized that writing code is one thing, and building software systems is a completely different thing. And it's not like it's harder. It's different in nature. It's a different thing. And you need different techniques. You need a different approach. Everything is different. And then I understand that one of the reasons why it's different, and you don't have to read any of those, I will make it short. The thing that is different, speaking about what you are just speaking, and thanks Andre or whoever made the order, but it was just perfect, The thing that we always thought is that, yeah, we have to write faster code, right? That would make us better if you write faster code. And meanwhile, I guess we all know that it's not about how fast we type, and that a lot of effort goes, and I will make the percentages right, depending on the various studies, 35%, 60%, 70%, doesn't matter. Everyone is saying a huge amount of effort goes into actually understanding to change. But sometimes, yeah, of course, in the end, it's understanding to change. But sometimes, just imagine you are new to an old code base, and you'll have to spend a lot of time in the beginning just to, yeah, understand. Of course, in the end, you want to make changes, but initially, it's just to understand. And then, of course, the other thing that I discovered was, this phrase that was very popular back then of technical debt. I'm not sure how popular it is anymore, but it was, everyone was speaking about technical debt back then. And the thing was with technical debt was that when you are at the code level, it very much is about, what Uncle Bob was telling us about clean code, the book, or you probably heard the phrase, right? Clean code, right? Yeah, everyone. Okay, and I hate the phrase clean code because the thing that it gives you the illusion is that basically all you need to do is to wipe it clean, right? It's something on the surface, like a table is dirty, and you just clean it, and then it's clean. And it might be true for code. I mean, for at the microscopic level, at the one-line level of code, it might be true. But when it comes to this difference between writing code and building systems, which involves very much a system-level thinking, it involves very much, yeah, the famous word design, then it's not anymore a cleanup, and it's not anymore about dirty code. It's about a disease. And you have to diagnose it properly and treat it. So for many years, I was just saying, oh, cool, let's measure software. Let's measure, we have cyclomatic complexity, we have lines of code, we have fan in, fan out, we have all those wonderful metrics, and then if you combine them, we could find some of those anti-patterns that, yeah, you might have heard of, got class and data class and blah, 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 all of those. And I did that for a long while. And then it hit me again. I got awards, I wrote books, I published tools, I did all of that. And then I realized, you probably know Forrest Gump, right? I'm not too old for that, right? I hope. Forrest Gump's mom was saying that life is like a box of chocolates. You never know what you're going to get. And software systems, the larger they get, they are more and more like a box of chocolates. And the strange part was, after I was so proud of my detection strategies for detecting design flaws and all that kind of stuff, and I got all my awards and all of that stuff, I realized I just failed. It doesn't work because the box of chocolates are so diverse. So I was back to square one, kind of, and the thing that I discovered was that the real technical debt, the real maintenance risks are not, most of them are not visible in the code itself. And that might be striking because you say, wait. It is in the code. The code is the only thing. I mean, I'm compiling, building, linking, whatever. It's the code. All the evil is in the code. I didn't say it's not in the code. I just said that it's not directly visible in the code. So then the thing is, where the heck is it visible? And this brings me to the second chapter of the presentation. It's just 3, don't worry. So it's what I call signals versus smells. Smells is, you probably heard the term code smells, right? It comes from Ken Beck. We'll come back to Ken Beck later, who was asked, when should I change my code? It says, it's like with small kids. You just change them when they stink, right? So that's a code smell. When should I change the code? When it smells. But do you know what? Going back to that thing that Ken Beck said, when should I change the code when it smells? What should I do with the code? Change the code. What I was doing for many years was just measuring the code. Here's the code and I'm just measuring it. But that's just the snapshot of what it is today. I could not measure change. And actually this brought this realization that there is a huge gap between what we analyze and what we need to know. Let me explain. We obsess, probably you don't so much in the front-end community or JavaScript, but the front-end in general, but in the back-end guys, we obsess a lot with cyclomatic complexity, you know, and we say we measure cyclomatic complexity, the nesting level of instructions, and then when it comes to modularity, we measure how many components depend on one other component, that one component on how many others it depends, and test coverage, not to mention, right? Everyone has a fetish with the code coverage, and is it green? Is it 100%? Is all of that? The question is why? Who cares about all of those? You say, yes, because we are professionals. Yeah, but who cares about it? Answer, nobody. And let me tell you why. We care about cyclomatic complexity because we say the more convoluted the code, the harder it is to understand. And the harder it is to understand, the harder it is to change. So the thing that we want to measure is change. That's what matters. Do we care about test coverage? Nobody cares about test coverage. What do we care about? Being embarrassed. The risk of a fatal a bug affecting production. I recently heard about a client who's in payments, and some code got accidentally activated. Some dormant code was activated by a feature flag or something, and they were starting to distribute money like crazy to various clients in a total amount of billions. They recover most of the money, but how does that happen? And that's the thing that I do not want to happen to me. So let's do more testing, but it's just a proxy. The same with modularity. I say, why do I care if a module is depending on so many others? Say, well, because if any of those change, then you might change. Why? But does it change? So the thing that we really care about is engineering cost and the product risk. Those are the things that we really care about. But for many years, we were unable to measure those. And because we were unable to measure those, we just said, let's use the proxies. We measure those, and yeah, it's the same. And it's not. So the good news is that we have things that we could fetch information from, like the source control system. This is, you just write a git log command with some parameters, and you will get funky blocks of text like this. And then you know that John Appleseed, right, made a change, and then we know what the change was about, which files changed together, all of that kind of stuff. You know that, right? And that's interesting because all those commits refer to files. And because they refer to files, I can connect them to my code. And the other thing is, the other source of information that we have are tasks in general. That doesn't have to be Jira. It can be any task management system. And the cool part is that increasingly so, when we write code and when we push a commit, we reference a task ID in the commit message. And when we do that, suddenly we have more than the code. And imagine now a model in which you could say, I start from the source code. Yeah, all those funky metrics, cyclomatic complexity, and all. I don't want to throw that away. At least not after working 17 years on that, right? So I don't want to throw it away. But but no, really, those are super valuable. But then the cool part is that we can go beyond, and we need to go beyond code analysis. And the cool part is that when we go beyond code analysis, I'll try to show you that we can start measuring the things that we really care for. And that's the fascinating part. And then we say, okay, we have the code changes. And as I showed you, because they reference files, we have a model where code files and code changes are linked together. But wait, then suddenly I also have the developers in the loop. So I would know the developers who made the changes on which files. I would know which files changed together, speaking about code change, right, and co-location. And then there is another thing, the tasks, right? And as I said, I can connect those by task references. So suddenly, I have a model in which I can talk about code, but I can navigate from the code to the changes and to the tasks. And it's one in one model. And that's the cool part. It's not statistics on Git, it's not statistics on Jira. I know there are tools that are doing that. The thing is, imagine a mental model in which you can navigate from code and ask who made the changes, which files were changed together, in the context of which task, or I select a task and say what's the impact of that code about, again, going to co-location, right? So I say, when I make this change, why do I care about co-location? It's about the impact of change. So we build this thing that we call Chronos, which is more like an approach. It's also tool-driven. We did a little bit of work with it. We just reached our 140th client, and we just surpassed 400 systems. These are all paying clients, right? So they pay for this service. And I want to show you a few demos of that, and then I will move to the last part, which is the most cool part. What you see here is a system. It's a very small one. It's an open source one. The problem is I would show you bigger systems, but the bigger systems that I have are from client, and because this is recorded, I cannot do that. Yeah. And what you see here is we call it a system map. Every rectangle that you see here is a file, and you will, of course, their size proportional to the size of the file in lines of code. And you see they have two different colors. The blue ones are those that were not changed over the last 6 months. Of course, you can configure that. The green ones are obviously changed. And then you see there's a heat map. So what the heck is that? In this case, it depends on the number of changes. So the darker the thing is, we just have 3 gradients because otherwise our brain would go crazy. There's a file, and then if I look at this one, these are dark blue, so it was changed a lot, but not changed over the last 6 months. Then there's this dark green one, it changed a lot, and it still continues to be changed. And this is just size? And it's not just size, because I have also the information of changes. And I say, let's find those that have 200 size and some cyclomatic complexity. This is static analysis. And then I see those, and I say, OK, these are large and complex files. But here's the thing. Even before I did this filter, I was mixing seamlessly information about change with information about code, like static. You say, oh, this is a large file. Oh, this is a folder. All this structure. But then the color and the heat map were about changes. So I was mixing the two. And now I said I put a filter, static analysis, lines of code, cyclomatic complexity. And then I said, yeah, but do I just care about large files that have some high cyclomatic complexity? Not really. So let me change that, filter and see what it says now. Changes for commits having message nature bug fix. You can read that, right? It's pretty easy to understand what it means, right? So it had many bug fixes. And it also has some strange anomaly that we defined that is called the task bottleneck. You can easily guess what that is. So because I have the information about tasks, I can see that a file was obsessively changed by many different tasks. And that's a problem because it's a coordination problem. And it's a real problem. That's the thing. As opposed to saying, oh, this is not cohesive, oh, this is too coupled, or so. This is a real problem. It really affects you. If everyone is changing the same file, every task is changing that, that's not good. And that even a manager would understand, right? And so we say, OK, let's move to the second example. This is structure relations. Again, static analysis, structure relations, point to analysis. This file X is depending on file Z. And you see they are grouped by some components, and you can't read it. When Andre saw the slide, said, you can't read that. I said, yeah, I know. That's the point. It's too complex. You can't read it. But let's see, OK, what we can do with it now. And you can simply guess what I will do with it. Now, it's both nodes, right, having size, boring, just more static analysis, more metrics, code metrics. But it just trimmed it down and I say, OK, now I have this. But now I want to highlight those that have both changes during last year. Because you remember we said coupling is important only if they change. But do they change? And now we suddenly see that from some of these, they do change. And now I'm doing something different again. What you see here are components. So they are grouped by components. Again, a structural element, a static element. But what if I would say, I have the commit messages. I know when they were changed. I know even the time zone when they're changed. So I would know if a change was made in Europe or in Asia. I wouldn't know if it's in Timișoara or in Cluj. But I would know if it's in Europe or in Asia. And, oh, sorry. OK, so I will have to, let me just, OK, here. Both nodes having blah, blah, and then I will, it will appear in a second. OK, so now I'm changing a different way of aggregating the whole things. And I would choose here the main geozone. Where is the main developer who made most of the changes? And suddenly it's Europe and Asia. And you might have noticed it's a different breakdown. There were more bad stuff in one component. Some of those are developed in Europe, all the others are in Asia. And these relations here, where both files are changed during the recently, and they are mainly developed in two different regions, they cause a real problem. I mean, they are more of a problem. So I went down from many files, many relations, blah, blah, blah. I trimmed them down, and then by combining them, I could find the things that really matter. I'm doing the same thing in reverse. Now what you see is not structure relations. Now what you see is what's called temporal coupling. So these two files are connected because they were changed frequently in the same commit. And then I say, oh, wait, so there are these two components here that are very tightly coupled. Or I mean tightly coupled, not very tightly. It's a neat system, so it's a small one. So, but you know what I'm saying. So now I want to, okay. So now I'll try to do the same, but in reverse. So I would say, I don't care about all of those. I just care about those that have a size that is higher than 200. They have more than a couple of changes in the last year. And then this time I didn't want to hide them. I just wanted to highlight them. And now I can aggregate them. So I would say, OK, don't show me the files because it's too much information. I want to see the components. But looking at the components like this is just stupid. So let's show it like a graph. And suddenly I'm reasoning about the dependencies, the temporal coupling, which is completely different, right? We never used to measure that, right? It was never a way of doing this. All we played was structure relations. And suddenly we have a view that is trimmed by combining all the time structural information, static analysis with metadata from the source control system. So basically what we did was we went from we have this code base. How do we understand it? Yeah, you just read the code. Oh, hey, stupid, that does not work, right? And then we said, well, we can use static code analysis. And of course, this comes with advantage. And we said, what if we just add all these evolution metadata, and then it's better? But the thing is this. I showed you various views. And I also added a few that I didn't show you, right? Like this one that you see all the time in your like a package explorer or file explorer, and then a C4 diagram or whatever. And they all have one thing in common. It's structure, structure, structure. Everywhere it's structure. And I know you love that because, yeah, we are all programmers, right? So we love structure. We love our technical components. They are our life. They are our world. So what's bad with that? Well, there's nothing bad, but going back to Kant back, if you don't read his blog posts, you should. They're really cool. They say our IDEs know about our code, but they don't really understand what we want to accomplish. We can rename variables, but they can also suggest better abstractions. And the thing is that they can't tell when our logic or the code logic is matching the intentions. The intentions? Whenever did we talk about intentions? Actually, we do all the time. It's just that it's in the planning meetings. It's once every 2 weeks. Then we talk about, yeah, what features, what, you know, and then it goes automatically. And then the thing that will make you probably all angry is that I would say intention goes over implementation. It's the intention goes over structure. And by intention, I mean business capabilities. I mean features. Can I reason about the code base in terms of business capabilities and features? You say, yeah, sure. I'm using a service-oriented architecture, and every business feature is in a service. Yeah, really. Are you all doing that? Are all the code bases that you work on with super service-oriented architecture where each service, each business capability is exactly in one module and only there, really? Then you are lucky. So my quest for software understanding added a fourth dimension. So we went from the first dimension, manual analysis, to the second one, which was static analysis, to adding history information and task information, so metadata from outside of the code base to enrich that. And now I want to add a fourth dimension. I want to understand what the system is all about. So we built another tool that we called chronologue, intentionally meant to resemble Chronos, but in a dialogue mode. I want to talk to my system. I will say, oh, now he starts with the AI bullshit. Yeah, bear with me, you will be surprised. So what we did is we start from the source code, we have some tools, boring stuff, doesn't matter. We extract relations, evolution metadata properties, and Chronos also helps us to do a component, file to component mapping. So we have all of that. And with that, what we do is we build a knowledge graph. Neo4j database, nothing special, a knowledge graph. But this knowledge graph has information about the file, folders, blah, blah, blah. Also the uses relation, the code change relations. Remember, I also have the structure relations, but I also have the code change relations. Imagine I could also add relations when two files or two modules are connected because the same developers are working on them or because they are obsessively changed by the same tasks. So I can add many types of relations between files and they belong to folders, blah, blah, blah. And then I add the history. Files, they belong to have changes, and changes belong to a commit, and the commit has a developer. So all the things I told you until now, don't forget it. It's all here. And then I have the system with the components that are done by someone who understands the system, and we have this model. And then we do another thing. We said, again with all funky tools, we built some code stubs. Code stub, meaning let me use this funky thing here, see if it works. So it says, this file has 400 lines, it was created, blah, 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 it was changed so many times. It is in relation with all these files. It is an orphan, a task bottleneck, it has a weak ownership, a critical weak coverage, and then it has all the import statements. Apologies, this is Java now, but I hope you don't kill me for that. And then I have the name of the class and all the methods, but guess what? There's no code. There's only the lines of code and cytochromatic complexity. I could add more stuff. But it's a code stub. And this code stub, I'm passing to a large language model. And I ask it, please, can you build a summary of that? I'll show a summary later in a second. And then it will build summaries for all files. And it will just enrich this graph database. A deterministic, that's the word, deterministic graph database. And it's just enriched with some information which is again constrained by all these things that we have here. It's constrained by the code. It's not like saying the large language model, have fun, interpret whatever you think this is. No, I'm not doing that because I think it's stupid. And then I have chronologue, just start chatting with the system. You may wonder how the heck does that work. Have fun. You don't have to read all the text. Oh, did it start? Oh, okay. So, first question. Explain what the system does. What are the top 5 business capabilities? Provide a one-line explanation. Just code stubs, no code, right? And it tells me, okay, these are the 5. It explains me blah, 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 all of that. Okay. And I see bad and word management. Okay, cool. Let's explore that further. And then I say map the business capabilities to the technical components. Suddenly, it's not like, yeah, I can check now if it's really service-oriented. Everything is in one place. And I would see some of the things are in one place, but then the bad and word management is split over various modules. And it even tells me what it does. What's the purpose of that module? How does it contribute to the functionality? And then, here's the thing. Oh, let me stop that. Create a priority list for new engineers starting to work on, oh, guess what? Our engineers, your colleagues, yourself, myself, we never started working on module XYZ or on file abc.javascript. We started working on a certain functionality. But you see why I said structure, 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 while the reality is completely different. So I said, he's working on bad management. List the 3 most relevant level 1 components. And for each one, the main folders that he should care about, and then also put the facts together. Oh, sorry. Oh, shit. I'm not good at this. Where's the videos? Sorry. Okay. Oh. Okay, so it will start giving me a list with the various things. We are not going to read through it, but just to give a sense of what I want to achieve here. And then I will go, and you see it tells me blah, blah. And look at this one. This is a fact. It found it in a knowledge base. Because I know what you are thinking. Oh, this is the AI crap where you don't know what's reality and what's not. It's very much constrained by the knowledge graph. By the way, thank you, Microsoft, for the concept of a graph RAG. We all heard about RAG. But it's not so frequent that people speak about a graph RAG. This idea came from Microsoft. I thought it will explode, everyone will do it, and it's just common sense. Nobody does it. Nobody does it. It's exactly that. It's as simple as that. And I said, OK, do a sequence diagram. And again, it will say, this here is an assumption. I don't want to show you sequence diagrams. I want to show you this difference, this interplay between facts and assumptions. And it would know because it knows if it finds something in the knowledge graph or if it doesn't, if it's just an assumption. So, and I asked it explicitly, please make the assumption explicit. So it said, these are the assumptions, these are the facts. And this is the other one that I love. Based on the past activity of developers, who would you advise me to assign to a certain task that would bring changes to patient bad assignment workflow? So within the bad thing, I'm interested in the patient bad assignment workflow. Who's the best to work on it? And it will give me this guy here because he has the highest total organic volume of change. You remember the information that I have from the metadata. And then it says, look, other developers are made also some other recommendations. And then I do something interesting that I didn't include in my architecture thing. I said, hey, Kronos, show me some relevant views of the systems with files and complex, blah, 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 with complex code. And then the first thing that it clicked on, I clicked on technically, is the temporal coupling, the component level, the one that I showed you earlier. So suddenly what I did, I showed you an analytical mind. I showed you Kronos, which was analytics. Various views, analytics. And suddenly I switched between the analytics mindset and the conversational mindset. Because I should never have to choose between those. We need them both while we reason about the software system. And the last thing that, sorry, I didn't stop it, but it doesn't matter. I showed you even the system map before, and then I clicked on one of the files there, and it gave me, and it will stop here. I can click on any file, I can click on any folder, and I get a summary of what's that. And the summary is not just about, its business capabilities. It's the features. It also gives me information, structure, architecture, all of that, but it's about features. And I can imagine having this at every level in your system. And then you say, yeah, but we have all these tools. And I will close my talk the way I started. I thought that I was the only stupid guy who is obsessed about writing code faster. It seems like 30 years later, there are even more stupid people like myself obsessed about writing code faster. And every effort that I see these months, how should I say, years, it's already years, right, is about writing code faster. And what about understanding? Well, there's not so much understanding happening because when you didn't notice when you played with, I'm sure everyone played, right, with having an IDE with, I don't know, GitHub Copilot or Windsurf with Cascade or whatever, blah, blah, blah stuff. It works well when your change has a narrow scope. You might not even know it has a narrow scope, but if the modularity is good, if things are collocated, it will find its way. It's not about in one file, as you said. It could be in multiple files. But the thing that we never say out loud is modularity. Modularity matters, and the size also matters. And the strange part with these systems is that the larger the system is, the more convoluted, the more non-modular it is, the more legacy it is, the more we would need tools that would help us to reason about it. But guess what? It's exactly those systems for which all these tools do not work. They work for nice and tidy code with good modularity. And there's one thing that I do not understand. This is Windsor, for instance. It doesn't matter. You could use anything else. I remember many years ago, Joanna is here in the room when we built in Fusion our tool. And we were using Eclipse. And we just wanted a parser. We didn't care about anything. We just wanted a parser. And I remember we had a chat, and you told me, we can't get the stupid editor out of that. Because although everything was so super modular and super, the editor was at the center of everything. 15 years later, it's still at the center of everything. You cannot get that damn thing out. And you say, why would you get out? That's where I do my work. No, you are not. That's what I told you. You're just using it from time to time. Most of the time, you're not using it. And then you'd say, yeah, but they have all these beautiful things where you can chat. Code or chat. And this is the thing that I wanted to show you. It's about the two things. I want to write, I want to understand. But it's just in a narrow corner. And then you might wonder, and I will show something that you will make you really angry as front-end engineers. There are some crazy people who started to create ugly things like this. Do they want to bring us to the Stone Age? Are those where we want to go? And the answer is no. But the thing that you see on the screen right now is the reaction to saying, stop putting the editor in front of everything, because what will happen in the future is we will have to focus more on system-level thinking, on designing the whole thing, on getting the bigger picture of reviewing code. And say, yeah, I don't want my code be written by agents. It doesn't matter. It doesn't matter. Beat your code. It doesn't matter. Code will grow and grow and grow. And as long as we obsess with writing, it won't end good, right? So this is a reaction. I don't think it will stay like that. I just imagine a world where all the beautiful things I showed you before will be part of your everyday life, where you can reason, but not on a large language model, gambling machine where you never know what the answer will be, but on a deterministic model where the large language models give all their power in the right place, but harnessed, constrained by deterministic model. And I found out recently that this has a name. If it's everything was about neural networks, this is about neurosymbolic AI. And I think, although everyone is against that, I think that's the future. And I will end with a quote from Ken Beck. Writing code is not anymore a career. And what is a career? Understanding, judging, seeing how pieces go together, and the wisdom to know what not to build. The funny part is that Kant said these words long after I accepted to give this talk with this title. Because I think that people all around the place have the same concerns and the same thoughts. And again, I hope you will not hate me too much, and I hope I didn't ruin any of your ideas about the future, but I hope that maybe in the 200th edition, we'll come back again and see if any of these became reality. Thank you.